We're going to move on to material for exam 9. And what you will find in Brightspace is the PowerPoints, right? PowerPoints like that. And you'll also find a review document that looks like an exam. And then you'll find the worked problems for that review document. Okay. Let's cover. This is the last chapter and the last exam, the last chapter exam for this course, CHEM100. And what we'll do is, this is Thursday. So next Tuesday, we'll do a review on this chapter. And the last exam will be due on a week from today, Thursday. And then the following week is the week before final exams, and we'll take both classes, both sections, Tuesday and Thursday, to review for the final exam. All right, so let's get started with chapter 18. Redox reactions. Redox stands for oxidation reduction. Okay. Now we'll need to, of course, define what that means. But the first thing you'll notice is this description is hyphenated. Oxidation and reduction always occur together, never occur separately. That's why we find them together in both the long version and the shortened version. So what do we mean by oxidation reduction? An oxidation chemical reaction is one in which electrons are transferred. Electrons must be transferred from one reactant to the other reactant in the process in order to complete the reaction. Our example here is sodium and chlorine. Right? That's the way that you will find them in their most stable form at room temperature and pressure. Right? Solid, gas. And when electrons are transferred, well, we find that what we get as a product is sodium chloride, table salt. But that doesn't tell you the charges, right? We learned how to do the charges earlier on in the semester when we were writing compounds, writing and naming compounds. And we learned that alkali metals are always +1 charge in a compound, and halogens are always -1 in a compound. But how did they get there? This shows you how they got there. This one is not charged, right? It's a metal. It's an element, pure element, no charge. Same thing with this one. There's no charge on those atoms. Now, if we look at them independently, we're going to find a bond between those two chlorine atoms. And we need 2 of these and 2 of those to balance the equation. And what happens is one of these sodiums transfers an electron to that chlorine, and the other sodium transfers an electron to the other one. So we get 2 sodiums that lose an electron, which makes them positive charge, and 2 chlorines that get 1 electron each, that gives each one of those a negative charge. That is a redox reaction. An oxidation reduction has occurred. Now, by definition, oxidation is loss of electrons. So that means that sodium losing an electron was oxidized. And chlorine that gained an electron is reduced. I suppose we can look at it this way. When something is reduced, it gets smaller, right? Okay, that's our intuition. Chlorine gets smaller in its charge. It goes more negative. And sodium, I don't have a good one for sodium. Sodium just loses an electron, it becomes oxidized. But they go together. And if you have trouble remembering the relationship between oxidation and loss of electrons or reduction and gain of electrons, there's a mnemonic called oil rig. Right? I think I've got it here. There you go. So if you just think oil rig, oxidation is loss. Oxidation is loss of electrons. Reduction is gain of electrons. Okay. Now let's try this one. In this reaction below, tin 2, right? We call it tin 2 because it has a 2+ charge, and tin is one of those elements that when it becomes charged can have 2 or more possible outcomes. Tin can be either 2+ or usually a 4+. It has those possibilities. So when we name compounds, we have to specify what the charge is. This would go into a type 2 compound. So what are we saying? Does tin gain electrons, reduced, oxidized, neither oxidized nor reduced? Well, the best way to look at that is what happens to the tin. If it's a 2+ charge here, and it becomes a 4+ charge there, we know that electrons have been lost. All right, we'll finish it out. Okay, so I like to use tie lines to show where and how many electrons have moved. So if we go from 10 here to 10 there, what has happened? In order to be more positive, 10 2+ must have lost 2 electrons. Right? So there's a loss of 2 electrons for each 10. Okay? There's only one of them. So 2 electrons were lost total for 10. Since oxidation must occur, now this is not part of the question, but I'm going to do it anyway. What happened to iron? What is loss? Oil. Oxidation is loss. That means tin was oxidized. Iron must be reduced then. And in order to go from 3+ to 2+, iron 3+ must gain 1 electron for each iron. But there are 2 of them. Equals 2 electrons total. And this iron must be reduced. Okay? Now, we'll answer the question in just a second. But notice, not only does oxidation occur simultaneously with reduction, the number of electrons transferred in one process has to equal the same number in the other process. So we have 2 electrons total transferred here and 2 electrons total transferred here. Now, what has happened? Well, we're saying 10-2 was oxidized. It lost 2 electrons, right? So A can't be it. It's not reduced, it's oxidized. Okay? That answers that question. Now, in order to follow the progress of electron movement, we need a way to determine what we call the oxidation state. In other words, in this case, the oxidation state is the charge. But there are some cases where you have redox reactions involving covalently bound compounds. You don't have ions. We still need a way to track the electrons. So we assign oxidation numbers to each of the elements in the reaction. That way we can track the progress of electron movement. Now, it's important that you recognize that this is a bookkeeping scheme. This is not saying that covalently bound elements are charged. They're not. But we do incorporate this into a bookkeeping scheme so that we can track the progress of electron movement. So we need some rules. All right. Rule number 1. The oxidation state of an atom as an element is 0. So what we're saying is if it's an element like this, or if it's an element like this, in its most stable form at room temperature and pressure. So we could have other things like, let's see, well, oxygen is diatomic also. Or we could have sulfur. Sulfur seems to be most stable like that. Each one of these has an oxidation state or an oxidation number assigned to it of 0. Okay? That corresponds to neutrality. If, on the other hand, we have a monatomic ion, like sodium becomes that ion, or chlorine becomes this ion, or oxygen becomes that ion, or sulfur becomes that ion, then the oxidation state or the oxidation number for that one is the charge. Now, when we move to covalent compounds, these rules become more important. So if oxygen is found in a covalent compound, such as water, the oxidation number on that oxygen is always assumed to be -2. Okay? So if the compound is neutral, what does that make hydrogen? Hydrogen would have to be a +1. Right? Because 2 times that would be 2 plus, and this would be a 2 minus, that would be 0. Okay? We've worked through these types of problems in naming compounds. However, there are situations where oxygen assumes a -1 charge, and those are peroxides. When you have 2 oxygens bound together covalently, and then you have some other group here and here, then both of these together are 2 minus. That means each one is a -1 charge, not charge, excuse me, a -1 oxidation number. Rule number 3. When hydrogen is in a covalent compound, and hydrogen is the first element, like this, it's always +1. If, on the other hand, hydrogen is bound to a metal, now hydrogen becomes charged, and it assumes the charge of -1. Because the metal has to be a positive charge, hydrogen has no choice but to be a -1 charge. Right? So our example there is aluminum hydride. This would have to be -1 because aluminum is +3. Okay, it's always +3. When fluorine is in a compound, and this doesn't matter if it's an ionic compound or a covalent compound, fluorine is always -1. Always, always, forever. So what would be for fluorine, we can have that compound. This is ionic because it's a metal nonmetal. So +1, -1. This would be, let's say, well, if fluorine were like this, it would be 0. But if fluorine were combined with, say, let's see, what would be a good example? Oh, how about like that? Then oxygen is a -2, fluorine is -1. But this is a covalent compound. I'm pretty sure it exists. Now, once we've tried to assign oxidation numbers to each of the elements in a compound, then the total of the oxidation states, the oxidation numbers, must add up to 0 for a neutral compound. So our first example, one example was this one, where we had 2- and +1, and I showed you that this 2- has to balance the 2+. 2 times a +1, right? So it's 0. But that rule holds for any compound. Right? Carbon dioxide. Oxygen would be 2-. So if this is a 4- total, then carbon must be +4, because +4 must balance to 0. That's how we determine the oxidation states for elements that have not been assigned oxidation states. Now, if you have a polyatomic ion, say nitrate, like that, well, we have assigned oxygen a -2 charge, or a -2 oxidation state. So 2 times 3 is -6. And what for nitrogen would give us a -1 total? It would be a +5, right? -1. So that equals that. All right. That's true for all polyatomic ions. We also assign oxidation numbers based upon their most likely charge in an ionic compound. So alkali metals are always +1. Alkaline earths are always +2. Right? Calcium, magnesium examples for alkaline earths. Aluminum is always +3. Gallium is always +3. Indium is always +3. Right? I left those out. Now, we may find ourselves in a situation where we haven't assigned an oxidation state for chlorine or nitrogen in covalent compounds. So when that occurs, and our example here is PCl5, right? We don't know where to start because we didn't assign oxidation numbers for either one of these. So when that happens, chlorine is given a -1, like the other halogen fluorine. So now we have -5, and phosphorus has to be +5. If we have nitrogen in a compound, we haven't assigned it, but if we say we have the cyanide ion, then instead of assuming something for carbon, we assume for nitrogen, it's a -3. Right? Because it is 3 positions to the left of the noble gases. You have fluorine, then you have oxygen, then you have nitrogen. Fluorine's -1, oxygen's -2, nitrogen would be -3. So if we sign -3 here, what for carbon would give you a minus total? A +2. Okay? Then we can deduce the other one. Okay, let's use these examples. Oops. And determine the oxidation state for each of the elements in the compound or the polyatomic ion, as the case may be. All right, K2 Cr2O7. You remember how to name that? This is a polyatomic ion. This is the dichromate. Polyatomic ion. And the dichromate, Cr2O7, has a -2 charge. Right? So that gives us an opportunity to solve this problem one of 2 different ways. We can say all alkali metals are +1. Right? So 2 times +1 is +2. That balances that +2. Now we can go in here and say, all right, oxygens are -2. So 2 times 7 is -14. And we need to reserve 2 minuses for the total. So now we really only have to balance a -12 charge with a +12. But there are 2 of them. So we divide by 2 and we get a +6. So this is +6, that's -2, this is +1. Okay, that's one way to do it. The other way is to just go straight across here for a neutral compound. Right? This is -2. Right? So let's make some room here. If that's -2, this is -14. This is 2 times +1 is +2. So at this point, we have a +2 and a -12. 14 is a -12, which has to be balanced by that pair of chromium atoms. So how do we balance there? That has to be a +12 divided by 2 equals +6. So each one of these is +6. Okay, and to check yourself, just go in here and say 2 times that is +2. 2 times that is +12. 2 times that is -14. So what does that equal to? 0. So we're good. There you go. Now we've got a polyatomic ion to look at all by itself. That's going to erase those. This is the carbonate, CO3, 2-. Okay, so oxygen is always -2, right? Times 3 is -6. we want to keep two of those minuses out for the charge. So we really only have to balance a -4 with a +4. So that makes this one, carbon is +4. All right. Manganese dioxide. Actually, it's manganese 4 dioxide. -2, -4, +4. So we would name this manganese 4 oxide. Excuse me, not manganese dioxide, manganese 4 oxide. Like that. And there are the charges. PCl5, we did this one earlier. This is one of those cases where you're required to assume chlorine is -1. -5 total, that means this has to be a +5. If we don't make that assumption that chlorine is -1, then we're stuck. We have no resolution to the problem. SF4 is easier because we actually did give a default value to fluorine, -1. So -4 total has to be balanced by a +4. Okay. All right, there's our example that we had before. Oxidation states, of course, going to be 0 for sodium, 0 for chlorine, +1 for sodium, and -1 for the chloride ion in that compound. Okay, we know that sodium, right? We already did this before. Sodium had to be oxidized. Oxidation is loss, oil. So sodium lost, which also made sodium a reducing agent. Let's put this one back up there. We can talk about it. All right, so we went from 0, 0, +1, -1. Sodium is oxidized. Right? Chlorine is reduced. Since oxidation and reduction always occur together, then one is responsible for the other one. What we're saying is sodium is oxidized, meaning it gives up an electron, which means it is the reducing agent. It causes the reduction of chlorine by giving it an electron. So this is the reducing agent. That means that chlorine is the oxidizing agent. It caused the oxidation of sodium. All right. Okay. Let's see. Here we have a combustion reaction. We have methane burned in an oxygen atmosphere to produce carbon dioxide and water. All of these compounds and elements are covalently bound. There are no ions here, but we do have a transfer of electrons. Remember when we were talking about identifying types of chemical reactions? One of the things we said was combustion reactions are redox reactions. And this is why. Oxygen is 0 from our rules. Oxygen element is 0. Hydrogen is +1. That makes carbon -4. Then on the product side, oxygen again is -1, -2 in both of those situations. And the carbon has to be a +4 in order to balance. And of course, the hydrogen is +1. So what happened to carbon? Let's put this one up here. Methane. Let's see, I think I need another marker. Right. Methane gas plus oxygen gas yields carbon dioxide gas plus water. Liquid. Oh, they're making it a gas. Well, that's all right. Means it occurs at a different temperature. All right. That was messed up. Let's try this one. Okay. So we've already determined their oxidation states. This one's 0. This one is +1. This one's -4. This one is -2. That one's a -2. That's a +1. And this is a +4. So if we draw the tie lines between the carbons, yeah, let's draw the tie lines between the carbons. Carbon. What happened to carbon? It was oxidized. It's a loss of how many electrons? We went from a -4 to a +4. So how many electrons do you have to lose to go to neutrality? 4 electrons will get you from -4 to 0. 4 more electrons will get you from 0 to +4. Right? So actually, there was a loss of 8 electrons for each carbon. And there was only 1 carbon, so we have 8 electrons total. Right? This is oxidized. All right. Now, how about oxygen? Oxygen went from 0 to -2, but it's in 2 locations. Right? It's in 2 locations. Let's see. Let's balance this equation. 2. So this oxygen went from here to here, and it also went to here. But in both cases, the oxygen is a -2 oxidation state. So we have gain, what? 0 to -2. 2 electrons per oxygen. Times how many oxygens? Well, 2 times 2 is 4. There's 2 here, 2 there, times 4 equals 8 electrons total. Right? And that means that this oxygen was reduced. Okay. Anytime you have identified the compound or the element that is oxidized, it becomes the reducing agent because it provides electrons to the other species. The O2 is reduced, and it is the oxidizing agent. All right, this is just a review. Redox means transfer of electrons. It may occur to form ions, or it doesn't have to, right? In covalently bound compounds, you don't have ions. So the movement of electrons can occur either in ionic type reactions or in covalent reactions. Oxidation means that you increase the oxidation state. We've increased from -4 to +4. It's gone from negative to more positive. That's an increase in oxidation state. And reduction is a decrease in oxidation state. It becomes more negative. All right. Okay, so we've got some sample reactions, I think, here. Yeah, we have to identify which of these reactions are redox And what are the oxidizing agent and the reducing agents? Okay. So the first one is zinc and HCl. Zinc metal plus hydrogen chloride in aqueous solution, which makes it hydrochloric acid. And they've been kind enough to balance the equations for us. Plus hydrogen gas. There we go. Now, later on in this discussion, I'm going to show you how to balance redox equations using a different method than the budget method. Okay, so is this an oxidation reduction reaction? There's a rule of thumb that can tell you if this is a redox reaction immediately. There's an element, right? We find that element in a compound over here, which means with this -1, this is +2. If you find an element in the compound on the other side of the arrow, that is a redox reaction. No exceptions. Or if you have an element in a compound here and it becomes excuse me, if you have the element here in a compound and here it's a free element, then that also is an indicator that you have a redox reaction. Right? This is -1 + 1, that's 0. Okay, those are all our oxidation states. Okay, which is the oxidizing agent? It's the species that was reduced. So which one is reduced? We go from +1 to 0. Hydrogen is reduced. Right? Which equals the oxidizing agent. And zinc was oxidized, which makes it the reducing agent. Okay? Here we go. Got a little animation going here. Okay? All right. That red means reducing agent, and that blue means oxidizing agent. So did we get them right? Reducing agent. Yeah, reducing agent, oxidizing agent. We're good. How about the next one? All right. So you'll notice that the way this equation is written, the left-hand side has an excess of 4 negative charges, right? You got 2 hydroxyls and 1 dichromate. All right, where are the other positive charges? Well, what we've done here is there are cations in that solution with dichromate and hydroxide, but they're just spectators. So we left them out because we don't need them, not to complete the reaction. So dichromate could have been potassium, could have been sodium. Hydroxide could have been sodium, could have been potassium, could have been any of the cations, alkali metals, or alkaline earths for that matter. But we don't need them because they're spectators. So if we write the equation as given, right, in aqueous solution, and then the hydroxides in aqueous solution, what are the products? Well, we get 2 CrO4, just the chromate in aqueous solution, right? And water. All right. So what are the oxidation states for each one of these? We did these earlier, right? This one is -2. This one's a +6. Right? Okay. This one is a +1, and this one's a -2. This one is a +1, this one's a -2. Oxygen's a -2. Times 4 is a -8. Hold 2 out, -6. This is a +6. Okay. So notice that none of the oxidation numbers have changed on either side of the arrow. That means B is not an oxidation reduction reaction. Okay. All right. Let's do the last one. C. All right. We have two CuCl aqueous. Yeah. And then on the product side, we have CuCl2. That's aqueous. Plus copper metal. What type of reaction is this? Well, what we've studied so far says that we go from a single compound to two different products. This should be a decomposition. Okay, what we also notice is we've got one situation on this side, right? -1 +1. And on this side, we have a 0 there, and we have a -1 and a +2 here. So apparently copper has gone two different directions. Right? One of these, like there are two of them. So one of these sends the copper this way. It goes to there, right? So that's oxidized. It's a reducing agent. And the other copper of this pair goes down here. Right? It goes from a +1 to a 0. So it's reduced. It's the oxidizing agent. Okay. It is a redox reaction. Copper 1 chloride is a reducing agent. Copper 1 chloride is an oxidizing agent. Okay. Now, one single CuCl is not responsible for both directions. You got two of them. One of them goes one way, one of them goes the other way. There's also another name for this special type of reaction. It's called a disproportionation reaction. The copper disproportionately moves. It goes to this one, and it also goes to that one. It's not equally proportioned to produce a single product. This one reactant produces two products. All right. Now we're going to learn how to balance equations. Balance redox equations. If I can ever get this board erased, it's being difficult. All right, hold on a second. Let's try this one. No, still difficult. All right. There we go. Take a little moisture. That's the trick. Okay. All right. Now we're going to talk about half reactions. What do we mean by a half reaction? Well, when we look at at a redox reaction, we've already shown that part of the reaction is oxidation and part of it is reduction. Only at this point, we've written it all in a single equation. But for purposes of balancing equations, we can separate those two equations out as separate equations. One would be the redox, would be the reduction equation, and the other would be the oxidation equation. And that way, it's easier to deal with balancing the overall equation if we can pull it apart and work with separates and then put them back together. So that's where we're headed. All right. So here's an example of a balanced equation. And we're going to show you what happens when we pull this equation apart into a reduction equation and an oxidation equation. First, we need to know what parts of the equation are responsible for oxidation and what parts for reduction. Okay, we've identified the colors here. The reduction equations are in red. So hydrogen and iron. No, we're not. Excuse me. I thought we were color-coded, but we're not. But what we have done is identified the oxidation states for all the elements. Okay, now that we know what they are, which species we're going to do which first? Reduction. Which one is reduced? Well, which one becomes less positive or more negative? Well, manganese goes from +7 to +2, right? It had to gain 5 electrons for each manganese. That means it was reduced. So we need to have manganese in the reduction equation, right? There's the manganate ion, and there's the manganese 2+ ion. Okay. We have to keep the water along with the manganate because manganate has oxygen in it. And we need a product that has oxygen in it. So we can't throw the water away. We have to keep the water for the reduction step. And of course, since water has hydrogen in it, we got to have hydrogen on the other side, right? The rules, right, conservation of mass still apply. You can't create matter, you can't create atoms, you can't destroy them. So if we've got one on one side, we have to have the same number on the other side. And that's what we've done here with the reduction step. And then we account for the electrons. So how many electrons did that one manganese have to absorb to be reduced? 5 electrons. 5 electrons will change the oxidation number for manganese from +7 to +2. Now what's left? What's left is iron, which is oxidized from a 2+ to a 3+. And it needs nothing else, right? There's nothing else left in the equation. So 5 iron 2+s will give up 5 electrons and yield 5 iron 3+s. So those are the reduction and the oxidation equations that can be extracted from the balanced equation that we were given. Now, that was going one direction. We're going to go back the other direction. In other words, we're going to be given a partial redox reaction, and we're going to learn to balance it. First, we're going to balance it in acidic solution. And then we're going to learn how to balance in basic solution. So acidic comes first. So you get the equation. You write the equation with the given reactants and products. Then you break it into half reactions. Then you balance the elements except for hydrogen and oxygen first, right? These are the steps. It'll make a whole lot more sense when I show you an example. Then we balance the oxygens using water. And then that means we've added hydrogens. So now we have to add hydrogens on the other side. That makes it an acidic solution when you have those hydrogen ions. Then you balance the electrons. And then you recombine the equations, but only if the electrons are balanced. So if you have 3 electrons in one reaction and 2 electrons in the other, you've got to multiply the whole equation through by some constant in order to balance the number. Then you can add it together. And then you cancel identical species. All right, so let's do an example. Here we go. Here we have dichromate. And again, we've left out the cations because they're just spectators. Dichromate ion, the sulfite ion yields chromium 3+ ion and sulfate ion. That's where we start. Okay, so we have dichromate. And we have, this is all aqueous solution, so I'm going to leave the aqueous out. Okay, and that gives us chromium 3+ and sulfate. There we go. That's what we're given. Now, how do we decide how to break this up? Well, you have to do the oxidation numbers first. Right? We've already done this one. We know the chromate starts out at a +6. And it ends up at a 3+. Okay. Sulfate, we have -2 for the oxygen, -6 total. We're going to keep 2 of those negatives for that. So we only have to balance +4. On this side, we have -2 times 4 is -8. We keep 2 of those out for the charge. That means we only have to balance a +6. All right. So let's see which one. Let me try to keep these in order. Separate into half reactions. Okay, it looks like we're going to go reduction step first. So we're going to take this reduction step out. So we have this one, 207, and we have a +6 here. And it's going to yield chromium 3+. That's the reduction step. So let's see. Yes. Now we're going to do now we need the oxidation step next. I may have this animation out of order. So let's get the oxidation step in here first. SO3 2-, this is a +4, yields SO4 2-, and this is a +6. Okay. Now we balance elements except for hydrogen and oxygen. So for this one, we need 2 chromiums on this side. There we go. I think that's what we're going to do next here. Yeah. There we go. Oops. Now, do we need to balance? No. 1 sulfur, 1 sulfur. That's good at this step. Next. Okay. Now balance the oxygen atoms. So how do we balance oxygen atoms? We balance oxygen atoms with water. So we have 7 oxygens over here. We need 7 waters on that side. right? 7 oxygens, 7 oxygens. All right. Now we have to balance how many? 14 hydrogens. So we put 14 hydrogens on this side. Right? Now we've got oxygens balanced, we've got hydrogens balanced for the reduction step. How about this side? Well, we've got 3 oxygens here and 4 over here. That means we need only 1 more oxygen. Right? Just add 1 more oxygen. That means we have 2 hydrogens that have to be added over here. Okay? So the oxidation step is now balanced for oxygens. Now we're balancing the hydrogens in my animation. Here we go. And it's good. Next slide. Okay, now we balance electrons for each of the half reactions. Let's see. Let's put our oxidation states in there. All right, so how many electrons in the reduction step, how many electrons did we have to add? Well, we went from +6 to 3+. So we have to add 3 electrons for each chromium, but there are 2 chromiums. So 6 electrons would be necessary, right? 2 times 6 is +12, +12, and 2 times 3 plus is +6. So +12 and 6 minus equals +6. All right? That's the reduction step. Now, how about the oxidation step? Well, the oxidation step says this goes from a +4 to a +6. So we had to lose 2 electrons. Right? If we lose 2 electrons from a +4, that moves it to a +6. We subtract 2 negatives, that leaves an excess of 2 more positives, +6. All right? And there we go. So now what we have to do before we can put these back together, this number of electrons and this number of electrons, one on either side, we have to reconcile them so that we have the same number of electrons, because you cannot have unbalanced electron movement. Right? What would happen if you had so many electrons moving from one side to the other, but the other side only needed a certain number and the others were excess? You would end up with a static charge. And we don't get that, not in chemical reactions. Right? Static charges for physics. So we have to balance the number of electrons that move. And that's what the next step is. So how do you do that? Well, we've got 2 electrons here and 6 there. So if we multiply this equation by 3, we'll get 6 electrons. And we can't just multiply 3 times that, because that says 6 electrons were lost here, and they weren't. There were only 2 electrons lost in this equation. So this ratio of reactants and products is now established. And the only way to change that value is to multiply or divide by the same number everything in the reaction. So now we have to do 3 times that. Okay? So let me do this. There we go. So 3 here, 3 here, 6 there, 6 there, and 3 there. And we use that up. Now we've got our electrons balanced, 6 and 6. Okay. Once we've done that, we can add them back together and give us the overall equation. All right. Now combine the equations. This is what the combination would look like if we just brought everything down. Add them down. And then what you want to do is cancel common terms. So, excuse me, we find out that we've got 3 waters on the left-hand side and 7 waters on the right-hand side. So if we've got, 3 waters here and 7 there, then that means we have 4 water total. Okay? Got rid of that one, and we reduced that one to 4. We got rid of the electrons, right? Because they balance both sides. We're going to keep this term, Cr2O7, 2 minus. How about hydrogens? We've got 14 hydrogens here and 6 hydrogens there. So all of those go out, and we have 8 hydrogens left. Okay. Excuse me. Let's see. Now we have 3 sulfites. Okay. And we have 2 chromium 3 plus. We've used up all the electrons, all the hydrogens, and we have 7 waters left over. Excuse me, we have 4 waters left over. And we also have 3 sulfates. So that should be the final equation. Balanced equation. So we have 8 hydrogens, yes. We have 1 dichromate. We have 3 sulfites. That's correct. Then we have 4 waters. Yep. 2 chromium 3 plus and 3 sulfates. All right. So that was this was the half reaction methods for acidic solutions. And the reason we can say acidic is because those hydrogens, that makes the solution acidic. So we got another one here. Cerium 2 plus and cobalt 2 plus yield cerium 3 plus and cobalt. All right, what's the coefficient in front of cerium 2 plus when we balance this equation? All right, this one should be a whole lot easier. In fact, we can use an abbreviated form of the half reaction method. And I'll show you that in just a second. As soon as I get all this other garbage off the board. I think the problem is this marker. These expo markers are very stubborn. See if I can find something a little more agreeable. What about a purple? We use a purple marker. All right, so CE. Yeah, that's not going to work. That's too light. How about a blue or a brown? That's better. Ce2 plus. It's cobalt 2 plus yields Ce3 plus cobalt. Okay. We could separate these out into half reactions and it worked just fine. But for a very simple setup like this, let's identify what happens to cerium. It's oxidized. There's a loss of 1 electron per cerium. And cobalt is a gain, 2 electrons per cobalt. Okay? Well, if we gain 2 electrons, that means we have to lose 2 electrons. So we need to multiply by 2 to equal 2 electrons. Times 1 equals 2 electrons. So if we multiply this one times 2 and this one times 2, that will give us 2 electrons for the oxidation step and 2 electrons for the reduction step. So now we know that the coefficient in front of Ce2 plus is 2. And one of the other reasons that we don't have to use the half reaction, the full half reaction method, is because we don't have any hydrogens, we don't have any oxygens to deal with. Now, we could not balance this equation using the budget method, because the budget method says there's 1 cerium here, 1 cerium there, 1 cobalt there, 1 cobalt there, and that's it, right? So we would assume, using the budget method, that this would balance, but it won't. It's not properly balanced because the electrons are not balanced. All right, so there we go. All right, here's another example. Now, do we need to use the half reaction method for this one? The answer is yes, because there is an oxygen involved. All right, so let's do that. All right, this is not working too well either. Okay. All right, just a second. Okay, we have bromine, bromide ion. Everything, let's see, bromine liquid. I guess we better put the phases in. Manganate ion yields bromine, elemental bromine, which is a liquid, and manganese 2 plus. Okay. So what's the oxidation step and what's the reduction step? All right, bromine goes from a -1 to a 0. That's the oxidation step. Oops. Okay. There we go. And the reduction step would be MnO4 minus yields Mn2 plus. Because this one goes from -2, -8, hold 1 out, -7, +7 to +2. All right. What do we do next? We balance the elements. Let's see. Let's do some animation here. There we go. Next, balance the elements. All right, have one manganese here, one manganese there. That's good. Here we have one bromide and bromine. That means we need two. We need two bromide ions. All right. Next, we balance the oxygens. We have one oxygen, four oxygens here. We need four oxygens on this side. 4 H2O. We don't need any for this one. There are no oxygens to balance here. Oops. Put the electrons in too soon. Well, that's okay. I'd rather balance the oxygens first. There we go. There, 4 oxygens. Now we balance the hydrogens. 8 hydrogens. Okay. Now we're going to balance the electrons. This is a -1, which means we've gone from a -1 to a 0. That means we had to lose 1 electron for each bromine. But there are 2 of them. So that means we lost 2 electrons. And this side we gain how many? Going from +7 to +2 is 5. We had to gain 5 electrons. For one manganese. So 5 is all we need. All right. Now we need to balance. Okay. There's the hydrogens. That's good. Balance the electrons. How do you balance the electrons when you have an odd number here and an even number there? Cross multiply. So you've got a 2 there. We're going to multiply this whole thing through by 2. And the 5 here, we multiply this one by 5. Okay, so that means this is 10. This is 5. And this is 10. And this one becomes 10. This one becomes 16. This one becomes 2. This one becomes 8. And this one becomes 2. Okay. So we used our multipliers. Now we have balanced electrons. And we can add the 2 equations together. Cancel common terms. The electrons, of course, are going to cancel. Right? We have a 10 bromines. I should say 10 bromides in aqueous solution. We have hydrogens here, no hydrogens up there. So we're going to add 16 hydrogens, 2 manganates. And on this side, we have 5 bromine, 8 water, and 2 manganese 2+. So let's see. Find a balanced equation here. 2 MnO4s, 10 Br, 16 hydrogens, 2 manganese, 5 Br2s, and 8 waters. So there we have a balanced equation in acidic solution. Now, how do we deal with basic solutions? The basic, if you know that your solution is basic, means that you don't have these extra hydrogens floating around. That means acidic. And in other words, you need hydroxyls. So what we do is we balance the equation for acidic, and then we convert it into basic. So here's what you do to convert to basic. You neutralize all the hydrogen ions with hydroxyls. So we'll take this one. We had 16 hydroxyls. That means we have to have the same number on this side. Okay? What does this equal? That's 16 waters. Remember? One hydrogen ion, one hydroxyl always equals a water. There we go. Okay, there's 16 waters with the hydroxyls and 8 waters. All right, then we cancel 8 waters on this side and subtract 8 waters from this side, which means 8. So now our balanced equation, now our balanced equation is 10Br minus 8 water, 2 manganate, 5 bromines, 16 hydroxyls, and 2 manganese 2+ ions. That's in basic solution. All right. So now that we know the difference between oxidation and reduction, and that always occur together, and we know how to balance equations that involve the transfer of electrons, what do you do with them? Right? If we put a reactant in aqueous solution with another reactant in aqueous solution, and electrons are transferred, then we get products. But how about those electrons, right? A moving electron is, in physics terms, a current. Right? Can we capture that current? Right? So that maybe we can use some of that energy. Because moving electron signifies energy. All right, as a matter of fact, we can. And what we do is we separate, not just on the board, separate the oxidation and reduction reactions. We don't just separate them on the board, we separate them physically in 2 separate vessels. That way we can access the moving electrons. That's electrochemistry. All right, when we do that, we can access, let's see, if we put, I'm trying to be consistent here. I may get it wrong, but if we have the oxidation step here and the reduction step here, and they're separate, now there's no reaction. In order for a reaction to occur, you need a complete circuit. So we're going to connect these 2 solutions through a salt bridge. And then we're going to have an external, we're going to have an electrode here and an electrode here. And we're going to connect those through a voltmeter. So we can measure. Now, what happens on the reduction side? If you have a complete circuit so that charges can move, then the reaction will run. If we break this, then no reaction occurs. Or if we remove the salt bridge, no reaction occurs. It has to be a complete circuit. So on the reduction side, what happens? Well, reduction is gained. So electrons have to be gained into this solution. That means electrons must move here. into that solution for the reduction to occur. And on the oxidation side, we have to lose electrons. That means electrons move out of this. So the electrons are moving this direction from oxidation side to reduction side. And since the charge, the negative charge is moving this way, we have to move positive charges back this way in order to balance the charges. Okay? So if we allow this reaction to proceed spontaneously, it will produce an electric current in that direction, a movement of electrons. Now, there's something weird about the physics of electricity. When electricity was being investigated in the, I guess the 18th and early 19th century, scientists incorrectly believed that the movement of charges in a conductor, like a copper wire, the movement of charges was the charges were actually positive. But once investigators determined that the structure of the atom, right, the positive charges can't move. Because if positive charges move, then you're disrupting the nucleus of the atom, right? Only the electrons move. So initially, the current was decided, the current would be going, and we give it this letter here, I. I equals current. The movement of charge, current is this direction. But the movement of electrons is that direction. Right? It's weird. But we're kind of stuck with it. But if the reaction occurs spontaneously, that means electrons will move this way to complete the reaction. We don't have to do anything. Just complete the circuit and the reaction goes. The other possibility, and this will produce a certain voltage, right? A certain push behind the electrons. And it varies depending on the reactions. If we want the reactions to run in reverse, in other words, now for this side to be oxidizing and this side to be reducing, what we have to do is insert something that develops a current in here, right? So that the electrons will now be forced to move that direction. If we can force the electrons, the voltage that we apply exceeds the voltage of the spontaneous reaction, then we can drive the reaction backwards. That's a non-spontaneous reaction. So we could do it either way. We can let it run spontaneously and we essentially make a battery. Or we can drive the reaction in reverse, and that is a electrolytic cell. Okay. The battery is also called an electrochemical cell. So in this case, we've got what? The electrons are on the left-hand side. They're being added into the manganate ion to produce manganese 2+ ion. That means this is the reduction step. We are reducing manganese in MnO4- to Mn2+. And the oxidation step shows the electrons on the product side. That's the oxidation step. If we put those two together, right, and in this case, we've got the reduction on the left-hand side, right? Each of these is called a half cell. And mine is backwards to this one. The example we're given here puts the reduction step on the other side. Right? So we have to complete the circuit. And that's where One possibility is a salt bridge, right? It is just a salt in solution and usually something to keep it from moving, right? We don't want to just dump the salt from the bridge into one solution or the other, right? That defeats its purpose. So we have two possibilities. You can either plug the hole here so that only ions will move out as required, or you can mix the salt in with agar, right? Anybody in microbiology knows that agar is a biological polymer that stiffens the liquid, right? It turns it into a sol and keeps it from moving. So we fill our salt bridge with that agar that also has the ions in it. And now the ions can move, but the bulk of the solution that's in the agar doesn't move. Or we can create a bridge by a porous disc. A porous disc does the same thing, only it's more efficient. And a salt bridge tends to add resistance to the movement of ions. But the porous disc reduces that resistance. It simply is usually a sintered glass disc that allows for movement of ions, but not bulk exchange of fluids. Either way, you get a completed circuit. This electrochemical cell or galvanic cell, then what we show is electrons now in this arrangement are moving the other direction spontaneously. And we exchange ions through the bridge or the porous disc in order to balance charges. So we don't get an unbalanced charge, an electrostatic charge. All right. Now, when we have the electrode at which oxidation occurs is the anode. So the oxidation side will give you an anode. And an anode is the location to which, a location to which anions move. So anions will be attracted to this one because we're removing electrons, making this electrode slightly positive. The anions move toward it. That's why it's called an anode, because anions move toward it. And the other one is a cathode, because cations move toward it, because they're moving in to accept those electrons, right? So the site of reduction is always the cathode, and the site of oxidation is always the anode. The cathode should be written on the right. So the picture here is wrong according to convention. Right? It should be this way. Cathode on the right, anode on the left. That's going to become important later when I show you the shorthand way to write these electrochemical reactions. I think I'm going to show you that. Let me see. Oh, no, sorry. In this course, we don't go that far. So this is picture time is the only way we deal with it in this course. Now, the other process, electrolysis, drives the reaction in reverse. And all you have to do there is to find out what is the voltage of this battery. What voltage would it produce? And then you introduce a current, a voltage, in the opposite direction of excess to exceed the spontaneous voltage, then you'll drive the reaction in reverse. And that's a process called electrolysis, and these would then be called electrolytic cells. A perfect example of an electrolytic cell is chrome plating a bumper. Right? They don't do that anymore. Not with our cars. Our cars are always, they have a steel superstructure surrounded by plastic. But when I was a kid, all cars had chrome bumpers. In other words, they had big, heavy steel bumpers attached to the frame of the car. And rather than leave the steel open to the atmosphere and so it could rust, then we'd coat it with chromium. And it did two things. It protected the steel underneath, and it made a shiny bumper. All right. So we're back to, electrochemical cell, lead storage battery. This is the battery that you'll find in most gasoline and diesel engine vehicles. A lead storage battery. The reason we use it is because it's, well, several reasons. It's cheap, right? Lead is very cheap. And we can make this battery out of cheap materials. Plus, they are recyclable. The one thing about lead acid batteries that's not desirable is weight. But in gasoline powered and diesel powered cars and trucks, the weight of the battery is irrelevant because we're getting our energy from the fossil fuel, not from the battery. Right? For electric vehicles, lead acid batteries would be impractical because they weigh too much. So that's why we go to a lighter version. Lithium ion batteries are the choice at present. Okay, back to the lead storage battery. The anode reaction is, right? And what happens at the anode? Oxidation. So the oxidation step, or the anode of this battery, is this reaction. We have lead, which is a solid, and it's submerged in sulfuric acid, a fairly concentrated sulfuric acid, actually. And it produces lead to sulfate. This is a solid, plus hydrogen ions and 2 electrons. Okay? So this is oxidation number 0. This is oxidation number 2 plus. Okay? Then the reduction side of the battery, which is the cathode, is shown in the next one. Here we go. Lead oxide. Lead 4 oxide, which is also a solid. And it reacts with sulfuric acid and 2 electrons and 2 hydrogens to yield lead to sulfate, solid. Oh, and water, excuse me, plus water, 2 waters. There we go. So those are the 2 half reactions in a lead storage battery. Notice that this is aqueous sulfuric acid. So both of these electrodes, this electrode at the cathode and this electrode at the anode, are submerged in the same solution, sulfuric acid. The beauty of this reaction then is you don't need a salt bridge because both of these electrodes are using the same solution to accomplish their reaction. And the consequence, the product is the same. Lead to sulfate. All right. So there's the overall reaction. lead plus lead oxide in sulfuric acid, now we have two of them, yields two lead 2 sulfates and plus water. Now, on this electrode, this product is being created at the electrode. It's a solid. So it's starting to coat your electrode and what we call occlude the lead underneath. And on the cathode, this lead oxide plate is also being coated with lead sulfate solid. And the lead oxide on that plate is being occluded by the lead sulfate. So when you charge the battery, then you drive the reactions in the other direction, right? You use the lead sulfate in either case to reconstitute these electrodes. That's why the lead storage battery is rechargeable. But here's the problem. Every time you recharge it, you don't change all of that lead sulfate back into that plate and that plate. There's a little bit left behind every time you recharge cycle. And over time, you build up lead 2 sulfate on the surface of the electrode. And at some point, you get so much on it that now the solution no longer has access to the plate underneath, to the material underneath. And you can't convert, you can't recharge it. It won't go back because the solution can't get underneath, down to the plate. Right? At that point, we say the battery is sulfated out. In other words, it's dead. It cannot be recharged. Yep. So when we recharge the battery, it's not a battery anymore. Now it's an electrolytic cell until we get it charged again, and then we can use it as a battery or an electrochemical cell. All right. The reason we spent so much time on that one, on the lead storage battery, is because it's so commonly used in our modern world. In fact, if you overcharge a lead acid battery, those hydrogens combine with each other, and the hydrogen ions combine and produce hydrogen gas. And that's why older batteries had these multiple cells, right? Because each cell is 2 volts. 2 volts. And if we chain them together, right? Chain them together like this. Right, so we have negative to positive and negative to positive and negative to positive. And we keep doing that. Then we have 2, 4, 6, 8, 10, 12. Let's see, positive here and negative there. So if you put cells like this in series, then you add the voltage. So 2, 4, 6, 8, 10, that's a 12-volt battery. Right? So what we used to do, because of this hydrogen buildup that inevitably occurs, is we had vents, little holes in the caps, so that the hydrogen could vent out. But when it did that, you also lost water, and you lost sulfuric acid in the process. So that's why you would pull into a full service station, and the service technician would come out and not just fill your tank, they'd pop your hood, and they'd open one of those caps and stick this device in there, suck up some of the solution into this device called a hydrometer, and test the density of your solution. And the density is correlated with the amount of sulfuric acid that's in your battery. And over time, the density would decrease as you lose sulfuric acid. So they would bring out some fresh sulfuric acid and squirt it in your battery and bring it back up to the proper level. Nowadays, the technology is developed so that those hydrogens that develop and produce potentially hydrogen gas are absorbed into a special matrix. And then when they're required to be released for recharging, then they're released from that matrix. So those batteries are sealed. You can't access them. And those are the types of batteries we use, for instance, in uninterruptible power supplies for our computer systems. And those lead storage batteries are sealed, which makes it safer, actually, because you don't have the chance of spilling sulfuric acid all everywhere. Of course, you don't want your battery to explode either. And if they get too hot or something goes wrong inside the battery, then they can swell. But that's not the common practice. Those batteries are usually very stable. All right. So let's go to what do we mean by electric potential, this voltage? Think of electric potential or voltage as a pressure, right? So if you've got a conductor and you've got electrons moving in it, there's a push. There's a push behind those electrons to get them from one place to another. That push is what we call voltage. And the electrons are flowing from the anode to the cathode, right? Because the anode is supplying the electrons as it is oxidizing, and it's going to the cathode where reduction is taking place and the electrons are being consumed. All right. Now, I mentioned this one already. The lead acid battery, each cell produces 2 volts of potential. And we string them together in series, we call it. Put them in series, then you can add the voltages together and you get 12 volts. Now, some vehicles require more volts. Like some large diesel engines will have a 24-volt battery, right? Because there's more resistance to turning the engine over. You need more voltage in your starter motor in order to develop that compression that will cause the engine to fire. Other types of batteries, we call them dry cells. They're not actually dry. The liquid electrolyte in them is contained in a paste, right? There's an acid version. Here's one example for a zinc anode. So oxidation occurs on the zinc, and reduction occurs in the matrix, in the paste, which has ammonium and manganese in it, the manganese dioxide. Right, that's one possibility. The alkaline version takes, let's go back. Right, the acid version has positive ions. I don't see any hydrogen ions in here, except for this one. That's an acid right there. The alkaline version has hydroxyls in it. So the zinc interacts with the hydroxyls and oxidizes. And then the manganate picks up those electrons and creates this Mn2O3. And it also has hydroxyls. Right, so the construction of the battery for the alkaline battery, let's see. Nope, this is the acid version. Yeah, this is the acid version. Because the reason I know that is because it has ammonium chloride in it. But the physical structure of the dry cell battery that you'll find in any store, D cells, C cells, AA's, AAA's, excuse me. These batteries The anode is the casing, the zinc casing, which has a plastic coating on the outside, of course. And then the cathode is a graphite rod. The graphite does not participate in the reaction. It's simply a conductor, right, to deliver the electrons that are produced by the anode from its reaction through the external circuit and then into the graphite rod, into that electrode. So the chemical reactions actually occur between the paste and the zinc casing. And the graphite rod is simply a conductor. All right, there are other types. The silver cell battery that you'll find in calculators and hearing aids. The mercury cell is not used anymore because of the mercury. But at one time it was commonly available. And you still have a cathode and an anode. Nickel cadmium. Now the zinc, the silver cell and the mercury cells are not rechargeable. Their physics don't allow for it. But the nickel cadmium battery was rechargeable at one time, and it preceded the lithium ion batteries. The problem with the nickel cadmium battery was, even though it was rechargeable, in order to get the full effect, the full capacity of the battery, you had to discharge it down to dead and then bring it back up. If you recharged it when it was only halfway discharged, it had what's called memory, charge memory. And it would think that its new location at half charge is now 0. So you would only have access now to half of what you normally had. And if you kept it under full charge and only used it periodically, eventually it would only run for a few seconds and then just peter out. So the way to get it back was to turn on your device and just let it run until it's completely discharged and then leave it there for a while. And it would go down to 0 again. And then when you recharge it, you get the full capacity back. But they were heavy also. Lithium ion batteries are lighter, plus they don't have that memory problem. They have other problems. Now, I think the last topic we're going to talk about is corrosion. What is corrosion? Corrosion refers to the oxidation of metals, right? In order for a metal to oxidize, let's use an example. Say iron. You make something out of iron pipe, steel, whatever the case may be. And over time, it oxidizes to, let's see, 3+. Okay, so that means it loses 3 electrons in the process. Well, then it's no good, right? This is just the oxidation step. So how do we get it there? Well, you need something, oxides, oxygen or sulfur usually, to serve as, this is the oxidation step. It's a reducing agent for something. So let's say it's oxygen in the atmosphere. Then you would have oxygen 2- over here. Okay. One of these, balance these two together. Well, we would have to have 3 electrons on this side for each of the irons, but you've got 2 oxygens. Well, I'm trying to balance it now, and it's going to be a mess. But to make a long story short, when metals corrode, the metal is oxidized. It loses electrons. and it loses its value. So one way, and this happens to most metals. Very few metals do not oxidize. Gold is one. It's called a noble metal. Platinum is also a noble metal. They tend to resist oxidation. So most metals will oxidize. Some of them very, very quickly. Right? Iron oxidizes slowly, and when it does, like iron plus oxygen yields Fe2O3. Right? So we need two of these. Actually, we need three. We need two here, and we need three here, and we need four there. Excuse me. This iron has a certain density. The iron oxide that forms from it has a different density. It takes up more space. So that's why when you see like a car in an open field that's been rusting for years, pieces of it are flaking off, because as the iron oxidizes, it expands and pushes away from the metal and exposes more metal underneath. Right? So it eventually just completely rusts away. On the other hand, aluminum will oxidize extremely fast. Right? Balanced the same way. The difference is aluminum oxide is about the same density as aluminum, plus it happens really fast. So what aluminum does is it forms this oxide coating over its surface. Any exposed surface forms the oxide coating, and it prevents water and oxygen from getting down to the aluminum underneath. That's why if you throw an aluminum can out, it'll be there 100 years from now. Right? If it's not disturbed, it'll be there because it forms that protective layer. Now, in the earth, we find aluminum oxide in an ore called bauxite. And bauxite is pre-processed at the mining site to give you as much pure aluminum oxide as possible. Then it's sent for processing. Okay, so we can prevent corrosion by several ways. One is you can coat the pipe, right? Just cover it with something. Paint it, right? Or you can dip it in zinc, right? You can, that's called galvanizing. You can galvanize iron. We used to have galvanized buckets, right? They don't use them much anymore. But it's just, you just take molten zinc and dip your steel bucket in it, and it protects underneath, because the zinc oxidizes more quickly than the iron underneath and protects it. Or you can paint it. You can alloy it. Right? If we alloy iron with manganese, right? And initially it was about 25% manganese mixed with the iron would produce stainless steel. Now we have various mixtures, different grades of stainless steel. And what happens is the manganese does what aluminum does. It oxidizes so fast, if you scratch the surface, it instantly seals with manganese oxide and protects the steel underneath. Well, actually, protects the other iron atoms in the alloy. This one shown in the picture is called cathodic protection. In other words, the cathode is, right, the cathode is the site of reduction. Okay. So reduction, if we, cathodic protection, in other words, we add electrons to the iron to keep it from being oxidized. So we transfer electrons from the magnesium to the iron pipe by means of a wire, and we let the magnesium become actually the cathode. Let's see. No, the magnesium is the anode because it is oxidized. The magnesium is oxidized and it's sacrificed so that we can deliver those electrons to the iron pipe. That's cathodic protection. We use cathodic protection in water heaters, right? Every water heater has an anode in it, right? And you can pull it out. It's a long rod. It's made out of aluminum, and it allows all the mechanisms, the iron and the copper mechanisms in your water system to remain metallic. We sacrifice the aluminum in that rod. All right. All right, which part is the cathode? The cathode is the site of reduction, which means the pipe is the cathode. And the magnesium is the anode. All right. Oops, I'm out of time. So when we do electrolysis, we're forcing electrons at a higher voltage backwards through an electrochemical cell and causing the reaction to reverse. So here's an example where we take water and we force an electric current through it, a direct current through it, and we need a little bit of acid added so the current will conduct, right? Pure water is an insulator. It won't conduct electricity. But if we can get electrons to flow through water, then we can, instead of the spontaneous reaction would be hydrogen, oxygen combining to produce water, as in many rocket engines. Right? The space shuttle used liquid oxygen and liquid hydrogen go into the engine and they're vaporized, mixed, and burned. That's the spontaneous direction. The non-spontaneous direction is to go the other way and produce hydrogen and oxygen from water. Right? This is the reaction that can occur in your lead acid battery if you overcharge it. This is also the holy grail of sustainable energy, right? If we can find a clean source of electricity, which is at this point, only nuclear power satisfies, right? The other sustainable forms of wind energy and solar energy are too weak. They cannot supply the needs that our modern society requires. So nuclear power would produce a steady supply of electricity economically, and we would use that electricity to split water. We would take the hydrogen and use that as a fuel. And that's the end of our discussion. So the next time we meet, which will be, this is Thursday, it'll be Tuesday, we'll do a review on electrochemistry using that review document.